This is Solve It for Kids.
Hello, my amazing and curious friends. My name is Jennifer, the Dean of all things STEM and STEAM, and this is Solve It for Kids, the podcast that gives kids and families a peek inside the real world of scientists, engineers, and experts as they solve problems in their jobs using creativity, cooperation, and critical thinking. And now please welcome to the show my podcast partner, Galactic Space Geek, Jeff Ganya.
Hello, Jennifer, and hello, listeners. Well, if anybody else out there is a Galactic Space Geek, you probably know that one of the most popular topics right now is way out there in space, and we have a great person to talk to about it today.
We certainly do. What problem are we solving today?
How do you study exoplanets?
Ooh, how do you study exoplanets? This is a really great question and one that is so timely right now. We're going to have lots of fun chatting about this. Who is our guest today, Jeff?
Our guest today is the fantastic Dakota Tyler. He is an astrophysicist and science communicator at DT Star Kid.
Welcome to the show, Dakota.
Hey, thanks for having me. Excited to be here. Always love to talk science and planets.
Oh, we are thrilled. And we're talking about exoplanets, not just planets, exoplanets. But what I want to start with is, as a kid, were you always one of those people that went outside and looked at the stars?
I wasn't really a stargazer, but I distinctly remember in maybe second or third grade, we had the unit where we go over the solar system. And I remember this picture of Jupiter that just had the black backdrop of space. And I think I always refer back to that.
Oh, wow.
I love that you remember one image that sort of stuck with you. So was it the planet itself that stuck with you, or was it the black background of space with Jupiter just kind of hanging out, not being held up by anything?
I think it was the background. Like, Jupiter is beautiful and it looks really cool, and it's this massive, interesting planet. Yeah. But the blackness back there, it's like, what else is there? There's the Jupiter right here. But like, what else is out there?
Yes, exactly. So how did you get from there? And I mean, briefly, how did you get from there to being an astrophysicist? Because that's a pretty big leap.
There was a very winding path, because I think that was maybe the last time that I thought about space for like 15 years.
Oh, wow.
I actually went to college and played football. So that's what I wanted to do. I wanted to go to the NFL, but I got injured and was trying to redirect and, figure out something else to do with my life. Right. And I got back into astronomy documentaries. And that's when I realized that there are more planets than there are stars. And it could be my job to study them.
And obviously, you just mentioned you got back into astronomy documentaries. Do you remember, was there something specific about there being more planets that caught your attention over anything else? There's asteroids, there's galaxies, there's black holes. What was it about
There's
that
dark
one
matter.
Yes. What was it about that one thing that you think caught your attention?
What's super interesting about planets is that I live on one. And so I'm sort of thinking what other possibilities could there be? What other life could there be? Like, do we even have enough knowledge to guess? What other life could look like?
Love that question.
Oh, yeah, that's cool. Okay, so before we go all the way there, we're talking about exoplanets. So it's possible that some of our listeners don't know what an exoplanet is. Could you kind of explain what that is?
Sure. So it's short for extrasolar planet, and it literally just means a planet that is orbiting some other star other than the sun. Right. When you look up at night, all the stars you see also have their own planets, and we just call those exoplanets.
Wow.
Okay.
That's kind of the keyword these days in astronomy and space, isn't it? Looking for exoplanets?
Oh, yeah. The field is really booming right now.
Okay, that leads us right into our main question for this episode. I know it's a big answer, You start wherever you want, Dakota. How do you study exoplanets that are so far away?
Yeah, it's a great question because it's not as easy as it is to study some of the planets in our solar system, where you can actually look up at night tonight and see Jupiter in the night sky.
Yes.
You can't do that with these other planets. They're too far away. Even with the most high-powered telescopes, most of them are way too far away for us to actually see them. So you have to rely on these indirect methods and sort of see the clues that the planets leave behind.
Okay. So is that through, like, say, some of the bigger telescopes we have, like the James Webb or the Keck or something like that? Is that what you're using for your research?
Absolutely. So most of the planets that we know of have been found through what's called the transit method. So you imagine, staring at a star and you're just looking right at it and you don't turn your telescope away. And if you stare at it long enough, you may see a planet cross in front of it. And you don't actually see the planet cross in front of it. You just see the star get a little bit dimmer and then return to its normal brightness. And then you keep staring and you see that it happens again and again. Maybe it happens every 10 days. One way to explain that is you have a planet that is on a 10-day orbit that is doing this very predictable dimming of the star. This is called the transit method. And most of the planets that we found basically doing just that.
Wow.
Okay. And how many exoplanets? I know it's not, you don't have to give an exact number. I know that number kind of changes basically every day now. How many exoplanets have been discovered now?
So we've validated over 5,500, but this is a very small fraction of the perhaps hundreds of billions that are estimated to just be in our galaxy, not even other galaxies, like just the Milky Way.
That's insane. So, can you talk to us about how the James Webb kind of helped us see further out and see some of these exoplanets?
Yeah, so James Webb has the ability to see literally just about as far as we can see in our universe and see like early galaxies, but it doesn't really have the ability to see planets in those galaxies. Those are too far away. But what it can do is it can look at planets that are in the Milky Way, some planets that are in our galaxy, and it can actually study the atmospheres and start to tip us off about what type of composition, what type of molecules are in the atmosphere, which is really interesting, again, for somebody who's interested in life. Like, does this planet
I was
have
just going to
oxygen?
say that.
Does it have H2O, carbon dioxide? Yeah.
Yeah, so isn't that like more like astrobiology, kind of where you're talking about how it's made and then whether or not life exists? Are astrobiology and astrophysics kind of getting melded these days?
Yeah, everything is sort of blending together. There's even astrochemistry. So you take, which is important, right? Because we need to understand like how these molecules are mixing and interacting. And then you have biology and astronomy. And so, yeah, astrobiology, astrochemistry, it's all like blending together now.
Whoa, that's cool.
Okay. You were just talking about how the James Webb Space Telescope can look at an exoplanet super far away, somewhere else in the galaxy. We can't see it with our naked eye. We can't even see it with our backyard telescopes, but it can see what the atmosphere is made of. Can you explain that a little bit? Because I want to make sure our listeners aren't seeing like it's not labeled. Like the planet doesn't have a little sign that says, I'm made of carbon, hydrogen, and methane.
Yeah.
How does James Webb know what it's looking at?
Now, it would be nice if that was the case. That would make our jobs really easy. So if you think back to that transit method where the planet is crossing in front of the star, right? And it causes the star to dim a little bit. And that's just because some of that starlight is literally being blocked by the planet.
Right.
Yeah.
But if you imagine on the edges of the planet, there is some atmosphere. It's like, it's not as rocky. There's actually some gas, the Earth has an atmosphere.
Right. Sure.
And so what happens is some of that light actually passes through the atmosphere and doesn't get blocked by the middle of the planet. And
Wow.
whatever is in that atmosphere, whether it was carbon dioxide or methane, it would absorb some of the light from the star. And then the rest of those photons would come to us in our telescope. And we can kind of,
Ah.
really what happens is the planet atmosphere sort of leaves a fingerprint on that starlight. And based on
Ah.
that fingerprint, it actually is kind of like holding a sign saying, hey, there's
Hey,
water
I'm
here.
here.
Hey, there's carbon dioxide. Yeah, because it's a unique fingerprint that only
Okay.
certain molecules leave.
Okay, so I have to ask, are you hoping one day to have a sign that says, "Hey, we're aliens, we're here," waving to you, right?
Yeah, well, that's what we're looking for. Something easy like that.
Do you expect to find that? I'm assuming no, because you
No,
still have to
well,
like decipher everything.
yeah. So you can start thinking about looking for complex mixtures of molecules. Like maybe it's
Ah,
not enough to find carbon dioxide because we know there's carbon dioxide on Mars or even
right.
Venus. But
Right.
what if you found carbon dioxide and oxygen and
Mm.
methane? You found a bunch of different molecules that are associated with life. You could say this could be a planet that has life
Ah,
that's producing these things, but you probably wouldn't be able to definitively say for sure unless you were to find something like, I don't know, some sort of technology or some radio communications or something like that.
yes,
But that's a bit
yes.
Okay.
different. That's a bit different than probing the atmospheres of planets.
Yeah, that's probably a much bigger level.
Okay. The main question is, how do you study exoplanets? And you mentioned that there are more than 5,500 confirmed. And obviously, some astronomers are still out there discovering more exoplanets. You were just describing how some astronomers and scientists are working on deciphering what those exoplanets are either made of or they have atmospheres. How does an astrophysicist decide what part of that they want to study?
Mm.
Like, is it just what you're interested in, or do you have to go find them first before you can get telescope time to figure out what the atmosphere is made out of?
You ask a really good question because a part of the answer there is what do we not know? What things do we
Oh,
not know?
Yeah.
And as we
ooh,
discover
what a
more
question.
and more, there's obviously more that we have answers to, but then you also end up getting these really interesting observations that don't have an answer. So, for example,
Okay.
one big revelation from the last 30 years in exoplanets is that we discovered that the most common planets in our galaxy, most sun-like stars,
Mm-hmm.
have a
Yes.
planet that is between the sizes of Earth and Neptune. So bigger than Earth and
Okay.
smaller than Neptune, and
Huh.
on an orbit that's closer than Mercury's orbit for us. So there's
Whoa.
a planet
Wow.
between those sizes and on an orbit that's less than 88 days. This is the most common type of planet that we
Whoa.
find. And we don't
Well,
have
Okay.
that in our own solar system.
no.
Right.
Does that tell you something, or we're still trying to figure that out?
Well, I think it does. I think it tells us that for our solar system, at least, is not the most common setup. It's not maybe that it's super
Oh,
rare, but it's certainly not the most common. It's not the most common thing that we see
okay.
out there.
All right.
And then we can start to think about, okay, well,
Yeah.
what kind of mechanisms is nature relying on and leaning on that's driving the observations that we see? Like, why? Why
Wow.
is it so common to get that setup in particular? When we
Good
go and
question.
try to figure out the experiments that we do, the planets that we want to study, you really are trying to come up with a nice experimental setup that can probe some question. And that's up to the astronomer. That's up to you to be creative, to
Yeah.
use the
Ah,
tools that we have
Right.
and the observational constraints that we have to try and answer questions because we can't go out there and I can't like put the planets where I want them to be. And you know what I mean? It's not
Or
like
bring
that
them
type of
closer so you can
yeah.
send a
right.
probe out or
Oh
something.
yeah, that would be so easy. No, we have to be really, really creative with how we set
Right.
these observations up.
Wow.
Okay. Our solar system is not necessarily the most common that's out there. We do describe the transit system. You mentioned if that star's light dims every 10 days, and Galactic Space Geek Jeff's brain went to Well, wait a minute. If somebody out there was looking at our solar system, the Earth is only going to block our sun once every 365 days. Like, you have to be the most patient astronomer ever. So it's probably good that there's a lot of planets that are in this 10 to 50 day, maybe, or at least closer than Mercury. I want to keep our talk on the exoplanets and not go off, but I need to ask, is it more common for those solar systems that have those super Earth, like not quite Neptune size exoplanets, to have a different type of star than our sun? Like, is it a much bigger or a much smaller star than we have?
That's a really good question because stars do come in different sizes. There are stars that are much, much smaller and cooler than the sun, and there are stars that are far more massive and hotter.
Right.
And from our observations, which are mostly of around sun-like and low-mass stars, it appears that for all of these stars, the most common planets are these, as you said, these super Earths or sub-Neptunes. Like they're the most common, and that is for sun-like, that is for a little bit smaller than the sun, a little bit bigger than the sun. Like they're very common planets.
So it seems like we're starting to learn a lot more. Why do you think it's important for us to learn about exoplanets?
For me, I think that it's fascinating that you can create all these different types of planets.
Yes.
Right. And something that always sparked my interest from the beginning is the potential of life out there. Like, is life something that is just unique to Earth? Is it something that doesn't happen anywhere else? Because I mean, that would kind of be fascinating if it were true. Like,
right.
What special thing happened here? But I think oftentimes in science, and especially in astronomy, what we find is that every time we think that we're the exception, we never are. Like Earth was not the only planet, right? We thought that the sun was the only star, but then we found out that it's not. There are hundreds of billions of stars. We thought that our galaxy was the only galaxy. We thought the entire universe was just the Milky Way galaxy. Right. And then we found out that there's trillions of other galaxies. So I suspect that life is happening out there in other places. And I really want to understand what allows that to happen. Like, what does that look like on other planets?
Yeah, and it seems like looking at exoplanets is the way to kind of answer your question, yes?
Absolutely. And you could even extend that to moons or exomoons.
Yeah. Okay.
Yeah. Now, we haven't detected any exomoons yet, any moons around other planets, any moons around exoplanets. But I mean, they got to be out there. We know from our own solar system that moons are everywhere.
Maybe we just can't see them yet. They're so small.
Oh, yeah. It's incredibly difficult. I mean, it's hard enough to detect planets sometimes. You know, detecting a tiny thing that's orbiting the tiny thing that you already can't see is it's a challenge. But I do believe that we will be able to do it.
Oh, that's fantastic. And we're getting into that point of mind blowing.
Yeah,
but
exactly.
I love the way you phrased that. It just keeps the answers that astronomy gives, just keeps pushing the envelope of, well, we thought this was the end. Oop, wait, it's not. We thought that was the end. Oop, wait, it's not. So there's probably going to be something next to learn. I want to jump back to something you said earlier on. As an astrophysicist, as a space scientist, you have to be creative. Can you give me an example? Can you tell our listeners, how do you be creative on, okay, these things are so far away. How do you be creative in how you are either collecting the data or looking into the data to learn something that we didn't know before?
Yeah, so it kind of takes a blend of knowing what instruments we have and what their capabilities are. Also, what the theories are, what the theories predict may happen or should happen.
Okay.
And then, is it possible to find some system that you can observe that would sort of take advantage of the instrument, take advantage of the theory, and try to tie them together, try to like tie this whole picture together. So, for example, I want to understand like how planets evolve. We know that planets evolve.
Okay.
Over time, their atmospheres get eroded by the energy coming from the stars.
Yep.
So this is something that we know happens. We can talk about it theoretically, but what you really need to do is grab observations of this. Like, let's prove that it's happening.
Okay.
We get that it's supposed to happen theoretically, but let's get some real observations. And so what you could do is you could think about an extreme example. What types of planets have a whole bunch of atmosphere that could get eroded away and are getting tons and tons of radiation from the star?
Yeah, right.
Okay.
What if you had a massive Jupiter-sized planet that was orbiting super close to the star on 3 or 4 day orbits? And there are a class of planets like this called hot Jupiters.
Yes.
And so we observe a hot Jupiter transiting, and we can actually detect its atmosphere being blown away in real time.
What?
Whoa.
Really?
That's amazing.
Yes. Yeah. This is my favorite exoplanet. It's called WASP 69b. A crazy name, but it's my favorite planet. It is a hot Jupiter, and it's having its atmosphere blown away, and the star is actually sculpting that atmosphere after it gets blown away into a comet-like tail that's over 300,000 miles long.
Wow.
Trailing the planet.
And is that going to continue as a comet, or do you see that forming something else eventually?
No, so, it's going to continue. It's a gas giant, so it's got tons of atmosphere.
Right.
And it's it only takes 3.8 days to orbit the star, so it's always going to be super close. So this process of losing some of its atmosphere, it's going to continue to happen.
Yeah.
And the star is going to continue sort of shaping that atmosphere after it escapes into a tail like that. So that's something that we would expect to continue happening. And if we wanted to test that, we could observe it again and see if indeed it is still losing its atmosphere in the same way.
Yeah. That's really cool.
WASP 69b. I'm going to look that one up. So in that WASP 69b solar system, do we know of any other exoplanets?
No. So that's the interesting thing about these systems that have a hot Jupiter like that.
Okay.
We're still trying to figure out exactly how planets form and how they migrate. But we know that something that tends to happen is when you have a big Jupiter mass planet, it probably forms further away from the star where it can have more ices. There's just more material out there.
Sure.
Yeah.
And you can imagine that as this massive planet is orbiting, it's like moving through this kind of debris disk of material, of gas and dust.
Okay.
And it kind of slows the planet down a little bit and causes it to migrate inwards. So if that's how you get a hot Jupiter, you can pretty much guarantee that any planets that are closer are going to get eaten up or knocked out of the way. They're kind of going to get bullied by that Jupiter, that hot Jupiter.
I love that description. Yeah.
Yeah. So there's no other planets in that system, right?
Okay.
And actually, interestingly, in our own solar system, there's some evidence that Jupiter was on a similar destruction path towards the inner solar system.
Oh, wow.
But through some interactions with Saturn, it actually kind of roped it back out and kept Jupiter at that further orbit, saving the inner solar system, but eating up some of the material that was going into Mars, which is why Mars is such a small planet compared to the other inner solar system.
Okay.
That's very intriguing. Oh my gosh.
Okay.
So, clearly you love and get excited about studying exoplanets and finding exoplanets. So what would you say to kids who are reading all these articles about exoplanets? And, what if they want to study that? What would you say to them? How would you recommend that they go about learning how to study exoplanets?
Yeah. So NASA actually has a lot of resources for kind of educating on what we know about exoplanets. NASA Exoplanet Archive, it has all of the planets that we have found and discovered. And there's a lot of really good space documentaries too that kind of talk about not just the exoplanets, but all of the discoveries that we're making in the universe. So I would continue, like checking on any documentaries and that sort of thing. I mean, you could follow there's a lot of good science communicators too.
Yeah, like you. Tell us where people can find you. That was a good segue there.
Yeah.
So my handle is at DT StarKid on all the platforms: Instagram, YouTube, TikTok. I do a lot of videos on TikTok, but I'm always talking about the newest discoveries. I'm always fascinated with
your videos are fantastic. I've watched them too. Yes. So it's not just for kids, right?
Yeah. Big kids and little kids.
There you go.
Yes.
There you go.
All right. I've got to squeeze this in before Jen moves us on. We are all going to go follow you. I love how you explain this stuff. It is terrific. Now, number one, I got to tell you, I am going to go to bed tonight wondering why our solar system is not the way it should be. Why is there not a hot Jupiter in by our sun? And how come we don't have a super Earth? But you mentioned your favorite exoplanet, WASP 69b. There's confirmed more than 5,500. Can you tell us one or two others that are really interesting that we should go take a look at?
Other exoplanets that are interesting?
Please.
Yeah.
So let's see. What are some of my other favorites? So I don't know if you're familiar with the TRAPPIST-1 system.
Oh, okay.
No.
So there's
But please.
There's this system called the TRAPPIST-1 system. It's a small star, a small, cool M dwarf, nowhere near as massive and nowhere near as hot as our sun. But it has 7 about Earth-sized planets, kind of Earth-sized to super Earth size.
Wow.
And sub-Neptune planets. And this is really interesting because several of them are actually in the habitable zone.
Wow.
Now, that doesn't mean that there's life there, and it doesn't even mean that it's actually habitable. But what it does mean is that they are the right distance from their star that liquid water could potentially exist on the surface, depending on what the atmosphere of the planet is like. And James Webb is actually looking at the atmospheres of each of these planets. And it looked at the closest couple already and didn't really see any atmosphere, which probably makes sense because they're a little bit too close to the star. But for some of the further planets, there's a possibility that it's going to look and see an atmosphere. And that's something that I would keep my eye on because this system in particular may be one of our best shots at seeing kind of an Earth-friendly atmosphere, at least in the near future.
Okay. Yeah. Oh, that's exciting.
Perfect.
I'm definitely going to go look this up. I think exoplanets are amazing and they're so much fun. And I'm like you, I'm curious to see like life out there and not even like human life, right? Like it could be something that we don't even know about. But I find that really intriguing. Oh my gosh. This has been such a great chat, but we are at the point in our show where we have to ask our guests to give our listeners a challenge. So I'm curious, what is your challenge for our listeners, Dakota?
Yeah. So, as astronomers, we're kind of tasked, and we talked about this a little bit, with using what we can see and trying to pull out information, trying to interpret what we can make observations about.
Right.
And I think a really cool experiment to do over the course of a month is to go out at night and draw the moon, draw what the moon looks like. The moon goes through phases. And if you draw what the moon looks like every couple nights, you can try to reconstruct where the Earth, the moon, and the sun are in the sky that would cause you to see the moon be lit up in that way.
I like that.
Because the moon is orbiting the Earth is orbiting the sun. And what you'll see is that the phases of the moon actually just align with the moon going around the Earth and the Earth going around the sun. And the sun is always sort of opposite to the side of the moon that is lit up. And sometimes that means we don't see the moon during a new moon. And sometimes that means we see all of the moon. And I think it's an interesting experiment to really get an understanding on how the Earth is moving through our solar system.
I mean, I love that because, I mean, I've heard the whole phases of the moon before, right? But I love that you're pulling out and you're saying, okay, tell us where the sun is, with respect to all
Mhm.
of that. Because all of a sudden you're talking geometry, right?
Yeah.
Like math, like understanding it spatially, not just looking at what you see. I think that's really cool.
And you're also adding the layer of turning everybody into an astrophysicist, like you talked
Yeah,
about before.
exactly.
You can't just go out and look once. You got to check that every 3 days or every 10 days. You need more data to compare with. And actually, I love that. That's great, Dakota.
Yeah.
Yeah. Yeah.
Well,
Yep.
this has been so much fun. Everybody make sure you go and listen to DT Star Kid. That is awesome on all of your platforms. But thank you so much for being on Solve It for Kids, Dakota.
Thank you, Dakota.
Yeah, thanks for having me. It was a blast.
What a super fun episode. As far out as we are studying and learning, we are still discovering exoplanets, learning what their atmospheres are like, learning whether or not they have compounds in them that could potentially support life. There is so much going on out there, and I love how DT Star Kid Dakota brought that challenge, actually 2 of them, right back to us. Number 1, over a month, go outside and draw the moon every night. If it's covered by clouds, just write cloudy, but draw it every night. And then the second one is when you go outside and look up, you're going to see one phase of the moon each night. Go back inside and on a piece of paper, reconstruct that Earth, Moon, Sun system based on the phase of the moon that you saw. I love especially that second one, Jen, because it really gets you thinking. When you're looking up and you're seeing the moon in a particular phase, you have to connect the dots on where 3 different celestial objects are. And that's how astrophysics gets started.
Yeah, it's also called geometry. So people can use their math. Everyone says, how do you use that math? I'm never going to use the math that I learned in school. Well, guess what? This is what astrophysics use all the time. And, it's really cool to think about it and then imagine how far away the moon really is. Everyone thinks you look up in the sky and it's right there. It's actually a fair bit of distance. Let's just put it that way from here. So if you do any of these things, we'd love to hear from you. Tag us on our social media. We're at KidSolve at Facebook, X, and Instagram. And don't forget to check out our website, solveforkids.com. And finally, be sure to check out DT Star Kid, which is where you're going to find Dakota. And he has tons of great videos and all kinds of things on Instagram and TikTok. So you can learn all about the science that he does every day, which is pretty incredible.
It truly is. And this is one of those episodes. Go back, listen again. There's a lot of science in it. And it will definitely make you want to do exactly what Jen and I are going to be doing in between now and the next. We will be watching DT Star Kid. Until next time, you'll hear Jen and Jeff on
Solve It for Kids.